Have you ever wondered how doctors peer inside humans without surgery to see what's wrong with us? Or how do they capture detailed images of our organs and tissues?
The answer lies in mathematics and medicine, particularly in magnetic resonance imaging or MRI. MRI is an advanced medical imaging technique that utilizes powerful magnets to generate highly detailed images of internal body structures. Physicians rely on MRI to examine soft tissues such as brain, muscle, and nerves to detect abnormalities like tumors or injuries.
In this video, we'll cover two major mathematical parts behind MRIs.
The Fourier transform is a mathematical tool used in signal processing and analysis to break down a complicated signal into a simpler component. The equation we will be using is g of f is equal to integral positive infinity and negative infinity times g of t times e to the power of negative I 2 pi ft times dt. The first part of the equation is g of f. G of f represents the domain frequencies shown by the signals. Integral of infinity and negative infinity is a mathematical operation similar to summing up all small components. The negative and positive infinity is a range of time going backwards or forward. G of t represents the time domain signal that we want to transform. E to the power of negative I 2 pi ft is a complex exponential function. Negative I represents imagery units. 2 pi is one full completed cycle over the interval of time we want to know. F stands for frequency and t is time. The last part of the equation is d of t. This signifies any small changes in the frequency.
Now let's dive into compressed sensing and MRI. Compressed sensing is a mathematical framework that enables the reconstruction of MRI images from undersampled data. In MRI, compressed sensing reduces imaging time without compromising image quality by exploiting spacing and compressibility. The equation minimized over x the norm 2 squared of ax minus y plus lambda times the 1 norm of x is a part of a long mathematical process in compressed sensing, but is one of the key equations. Min or minimize means we're trying to find the smallest value of this function, and x is our signal. 2 norm squared of ax minus y plus lambda is the square error norm, representing how close our predicted measurement ax are actually to the measurements of y. Lambda is parameter that balances the error term with the sparsity term. 1 norm of x represents the sum of absolute values of the elements in x. This equation overall helps us find the signal x that both fits the MRI data closely and remains sparse, allowing us to use fewer measurements while still producing high-quality images. Overall, these are two important mathematical parts behind MRIs.